Hello, shall we start?
Yes, sir.
Okay. So, in continuation with earlier rule, last time we have seen perceptron learning rule, where rule is d minus o. So, change in weight is given by CRX. Now, if you see carefully, what is happening is you compute net here, then you pass on this to activation function, and then you compute output. This output is compared with desired response. So error signal d minus o is computed. This will get multiplied with input and learning constant. So change in weight in total is given by c into d minus o into x. So this is what perceptron is doing. Now next learning rule is called as delta learning rule. This is the most popular rule and most useful. So rule is d minus o. So this is nothing but o into f dash. So this f dash stands for derivative of activation. Now see, change in weight is given by c into d minus o into f dash into x, that is input. So this is your x. You compute net here, you pass on net to activation function, and it will give you output. This output you will compare with desired response. So d minus oi, that is difference, you will multiply with f dash of net, that is derivative of activation function, and that becomes your rule. This gets multiplied with input x, learning constant c, and this is a change in weight according to the error signal. Now compare with earlier one, change in weight is equal to c into di minus oi into x, which is perceptron. The only term which is getting multiplied is this new term f dash. Now how this is obtained, or why this f dash is coming into picture, that we are going to see. The basic of this is the gradient of function, scalar function. So del dot f. What is gradient of a scalar function? Anybody? As it is written here, the gradient of scalar value differentiable function is a vector whose value at a point P is a vector whose components are partial derivative of f at P. So gradient of function f at P is given by df by df derivative df dx1 df dx2 df dx3 and so on. So this will continue depending on dimension. If there are n dimension, then this will be dou f by dou xn. Okay. Now, what is physical meaning of gradient? Now, assume this is a small mountain and this is the peak of mountain, highest point, and this is some axis. I can say x, and this may be y direction. So height is a scalar function. There is no direction. Okay. Now if you see from top, so this will look like this. So you have this x1 direction and this has suppose x2 direction. So you can suppose I choose this point, you can easily tell me the coordinates of this particular point by measuring this from the origin, say maybe 25 meters here, maybe 15 meters here. So this point becomes 25, 15. So like that we define the coordinates. And height of this is, if this is the point P, then height of the mountain at P is h of P, which is equal to maybe some, say 100 meters. So like this, if I choose any point, say this is P2, then it will have its own height from the ground level. So if we collect the equi-height points of the mountain, then this is the ground level and this is the peak, max. So minimum and maximum. Now if I draw equi-height or join all the equi-height points, this becomes locus of that particular point, for that particular height. Now what gradient is doing, if I take this function height, the gradient is giving you direction from given point to maxima. Suppose you are standing here. If you find gradient of h here, then this will be the direction of the gradient vector. If you stand here, then this will be direction of L dot H. So note that gradient, that is differentiation with respect to x at a given point towards maxima of that function. Is this concept understood? Anybody?
Yes, sir.
Okay. Now assume there is a mountain of error, because in neural network we want to minimize error. Assume that we want to minimize error, and these are the error surfaces like this. So error is like this. So there is a mountain. So error here is highest, error here is highest, and here is low or minima. Now when you stand, suppose at this point, and take gradient of error, obviously it will show towards maxima, because this is maxima. But we want to travel towards minima. Okay, we do not want to climb the mountain of maxima where error is increasing. So this side is error increasing. And this side is error decreasing. Now the variables that control my error are these weights in this case. In case of the mountain, we were having the coordinates x1, x2 as the parameters. Now here we control the height of error by changing weight. That means, suppose you are standing here, a point P is defined by weight W1 and W2. Let us take a neuron which has weight W1, W2, some input x1, x2 is going, and there is some desired response, there is output, and you are computing some error. So error here is difference between desired response and actual value. So actually the error is defined as error is half t minus o square. So this is a squared error. So we'll see details again. For time being, assume that this is the point P and you're standing at P by choosing W and W2 as your parameters of neuron. Okay, and error is E. So if you compute gradient of error here, then it will point towards the maximum of error in this direction. But you are interested in minimizing the error, so you want opposite direction. So what trick is done? We take a negative gradient of error. So negative gradient of error is a key thing in neural network. Okay. So if you travel with negative gradient of error, so you are moving in this direction. So you are now with a new point P2 with this much of error. Then again you compute gradient of error. It will then you take negative, then you will travel this side. So ultimately, if you go on traveling in the negative gradient direction, you will land to minima. Now there is no point below this surface, so network will settle here. So that is the minimization of error, and we call moving this point from this minimum point as training of network. So this is showing same thing. So if you stand here, say here, then this is maxima. If you stand here, this is maxima, and this is the minima which we want to achieve. So when I do random assumption of weights in a network, that means I randomly choose a point to start with. Maybe if I stand here randomly, then this much height of error is achieved. If I stand randomly here, then this is the error achieved. If I stand here, this is the error achieved. If I stand here, then this is the error achieved. Now, with a given point, we will travel always towards negative error direction, negative gradient error direction. So as to reach somehow with minimum error. Obviously, when you start with this point, reaching this point will take time. So this point to this point will take time. From this point, we can reach quickly to minimum. So depending on where your random assumption starts, neural network will take accordingly that much time. Now note down this derivation, small derivation, carefully. This is the key thing behind the popular neural networks. You take anything, it will land to gradient of error. Now this is gradient of error. That means we are interested in error. We want to minimize the error by controlling the parameters W. W is the controlling parameter, which your algorithm will change to reduce error. So let the error is defined as, so I should put here a small triangle. This means error is defined as half di minus oi square. So we are trying to reduce squared error. Why to make a square? The reason to make square is that we will always get difference positive. Okay, so sometimes your desired response is suppose -1 and you are obtaining say +1, then d minus o is equal to -2. If desired response is +1 and you are obtaining -1, then this is +2. So error is always plus or minus 2. If you obtain the correct answer, then error is 0. Now what we do, we square this error so that if even the error is negative or positive, it is error. So we make square of that. And half is just for adjustment purpose. Now if you differentiate error with respect to w, j, this j stands for weight of jth terminal. Okay, say this is a ith neuron, so its output is OI, its desired response is suppose DI, then this is X1, this is X2, this is suppose some intermediate XI, then there is a weight suppose WJ here. I should not confuse with this I and this I can call this as suppose K, let it be I. So we want to update this weight. We want to find out relation between change in this weight with respect to the error. So we differentiate the error with respect to Wj. So we take this error function. There is some problem. Check. Okay, so next step is this one. Now can you simplify this further? So this 2 get cancels. Di minus Oi into so Di minus f of W transpose X. Okay. So this you can write as D minus OI into f dash of W transpose X into, in this case, X, I think I have called K. So this is change in the error with respect to Wj. Now if I do this partial differentiation for j equal to 1 to n, that is for all weights, then I can write this as, now remember this is a vector, W is a vector, so this will be di minus OI into f dash into X. So this is called a gradient of error. But we want negative gradient of error. So negative gradient of error, so that minus sign will go, and your change in weight now will be, so I can write here, negative gradient of error. So this we obtain as change in weight is equal to some learning constant. Sometimes I write C. So di minus y f dash of net to x. So this is my change in weight, which is say delta learning rule. Sometimes it is written as delta LR. So this is a key rule. Even your deep network will use delta. Now take this problem. Find f dash of h, f dash of x of tan hx. That is bipolar sigmoidal activation function. Now your bipolar sigmoidal activation function or tanh function can be written like this. So 2 divided by 1 plus e to the power minus net minus 1. So this is actually obtained from sigmoidal activation function. What is sigmoidal activation function? It is 1 divided by 1 plus e to the power minus net. So I am multiplying that by 2 and subtracting 1 from it. So the sigmoidal is in the range 0 to 1 like this, as shape function in the range 0 to 1. If I multiply this by 2, this will be 2 and subtract from 1. So it will be same shape in the range minus 1 to plus 1. So that is what is happening. Now try yourself. What is f dash of this? So if you do differentiation of this function with respect to net, you will obtain this quantity. Now you solve this thing, 1 minus o square into half. What you do, you substitute o is equal to this thing. So half into 1 minus o square, you substitute value of o here, then square it, and you try to solve this. So this will also result into 2 into e to the power minus net divided by 1 plus e to the power minus net square. So these two things are same. Meaning is, given a neuron, if you substitute activation function as tanh, you compute O and you require f dash to compute change in weight. It's very easy. F dash is equal to half into 1 minus O square. Suppose this is 0.7, then f dash is half into 1 minus 0.7 square. That's all. So beauty of these equations are, once you obtain its value, you easily obtain its derivative value. And when I want to use this function as activation function, I can easily substitute in my change in weight equation the corresponding terms. So change in weight becomes very easy if I use sigmoidal or bipolar sigmoidal activation function, tanh function or logistic function. So if I use the logistic function or sigmoidal function, you see this is f dash. So f dash is equal to O into 1 minus O. That means O is suppose 0.7, then f dash is 0.7 into 1 minus 0.7. Right. So let us take, I think, one example so that these things are more clear. So these are 3 training samples. Let us choose learning constant as 0.1. These are corresponding desired response, and this is initial guess. Now with step 1, your input vector is x1, your initial guess is w1, then you compute net1. So w1 transpose x1 is 2.5, then you compute output using the activation function as bipolar sigmoidal or tanh. Then it is 0.848. Use f dash of net. So f dash of net is equal to half 1 minus 1 square equal to 0.140. So this is my first computation for change in weight. Now I update the weight using delta learning rule. So this is the delta learning rule. C into D minus O into f dash of net x. So if I substitute proper values and then add to my initial guess, I get W. Now I take this W2 in next step here and take second training sample. I compute net 2, which is minus 1.948. So I put into again activation function, it gives me minus 0.75. Then I compute f dash and it is 0.218. Then I update weight by adding to W2 the current change in weight. It gives me W3. Now this W3 you multiply with X3, the third input. You compute net 3. Then you put into activation function. It gives you 0.842. You compute derivative as 0.145 and then you compute W4. So this is W4 resulting after first iteration. Now what you can do is you compute error here at this point. Okay, for the training samples, you can do a sum of equal to 1 to say capital N total number of samples di minus oi. You can take square of this. You can just say half. If this error is less than a required threshold, then you stop. Otherwise, you go on updating the weights. Sometimes you may not achieve the required error by iterating so many times. So you can, in program, you can put a seal on your number of iteration using say a while kind of loop that you will not cross 1000 iterations or 10,000 iterations and so on. So details we will see in subsequent lectures, but in a nutshell, this is how delta LR works. Any doubt here? Is this fine? Ganesh?
Yes, sir.
Okay. So we will stop here. Then we will see next time unsupervised learning rule, that is winner take all. Okay, thank you.